Prove that for any sets A, B, C, and D, if A times B and C times D are disjoint, then either A and C are disjoint or B and D are disjoint. Alright, let's try and sketch this out. So we might have a set A and a set B here, whose Cartesian product can be represented by this rectangle, including the interior, and then a C and a D. Okay, so maybe C could be here, and D could be here, and then C times D would be this rectangle. Okay, and indeed I've drawn A times B and C times D so that they're disjoint. We label those A times B, C times D, and in this case actually A and C are disjoint and B and D are disjoint, right? There's no overlap sort of between the x coordinates, if you like, or the y coordinates of points in these two rectangles. However, there are other possibilities for C and D, which would still keep A times B and C times D disjoint, right? For example, C times D might have stretched over here, right? And it would still be disjoint from A times B, but in this case, C would overlap with A, and only B and D would be disjoint. Okay, or alternately, this rectangle could stretch down this way further, which would mean we're stretching D so that it overlaps B. So those are no longer disjoint, but A and C would still be disjoint. Okay, as soon as you try to sort of grow both of them, right, grow in both directions, then right, if A and C overlap and B and D overlap, then your two rectangles A times B and C times D are going to overlap. All right. Okay. Well, that's sort of what's going on. So let's try to write up a proof. Given and goal, I've already written out. Okay, here's that these two sets are disjoint, and that implies that A and C are disjoint, or B and D are disjoint. Okay. Well, we got to choose direct proof or proving the contrapositive, and you have to ask yourself: would I rather prove things about sets being disjoint, or about them not being disjoint and overlapping, right? And I chose overlapping because if two sets overlap, that means the intersection is non-empty, and that means I'm going to have some actual points to work with. Okay. So I'm sure you can prove it either way, but this is the way that I chose. So I'm I'm proving the contrapositive of this. Okay, so I have a couple negations, and let's see, the negation of that disjunction, I'm going to use De Morgan's law and get a conjunction. So this says that A and C have a non-empty intersection, and the intersection of B and D is also non-empty. And on the other side, well, the negation of that's just an equality of two sets, right? So I just say, okay, the sets are not equal. Good. All right, well, we have a conjunction. We can write the two statements on separate lines. We know they're both true. And over here, we'll just keep it like it is for the moment, okay? And then let's write out the definition of what it means for A and C to have a non-empty intersection. It means there exists some x, which is in the intersection. And similarly, there exists y, which is in the intersection of B and D. And similarly over here, for these two Cartesian products to have a non-empty intersection means there exists some p, which is in the intersection, which is in both. Okay. We can do some existential instantiation with our givens to get an x naught and a y naught. And then over here, it looks like, okay, we have some free variables x naught and y naught, so probably the p that we want to prove this for is the ordered pair x naught, y naught. All right, so let's prove the existential in that way. So we just need to recombine this stuff in the right order here. Break up the conjunctions, and the same thing over here, right? Just using the definition of intersection. And, well, that does it. If you just look at this, we have x naught is in A and y naught's in B. That gives me x naught, y naught in A times B. And then using the other two statements, I get that x naught, y naught is in C times D. Good. So let's try to prove this thing. Remember, the first thing we did was to try to prove the contrapositive. So the consequent here, or rather its negation, came over as a new given. Okay, so we'll say suppose that, and that's a little bit hard to write out in English, so maybe I'll go ahead and write out the next line, which then got broken up like this. Okay, basically we're assuming that A and C are not disjoint. So A and C are not disjoint. And moreover, B and D are not disjoint. And we're going to show that, well, that A times B and C times D are not disjoint. Oops, and went off your screen there. And C times D are not disjoint. Okay, good. So, well, what do we know? If these guys are not disjoint and are givens, then we have this x naught and y naught, right? So let's take our reader up to that point. So we know there exists some x naught in A intersect C, and let me just put these on the same line, and some y naught in B intersect D. Okay. And then, okay, we've got definitions of the intersections there. And then, as I mentioned, we're going to just combine these to get here, and combine these to get here. And those together will take us up to our goal, which was right there. So we should say because x naught is in A and y naught is in B, it follows that x naught, y naught is in A times B. And then I'm about to say the same thing, so let me copy and paste that. But this time I want to see, because x naught is in C and y naught is in D, it follows that this point is in C times D, right? Okay. And if it's in both of them, then, well, then you get back here and it's in the intersection. Okay, so we should say, therefore, based on the previous two lines, x naught, y naught is in A times B and in C times D. So this intersection is not empty, therefore those sets are not disjoint. Okay, so just remind our reader that's where we're headed. So A times B and C times D are in fact not disjoint. And that does it.